Hello, thanks for stopping by. Today's video is going to be really long, really boring for the last half of it, but if you stick along, it's 3 parts. First part is the general concept of irrigation. The second part is where I go over my actual system that I purchased and put together. And then the last part's going to be all the maths and the figuring out for doing the calculations for how much water the system can hold and go through. And that's going to be it. Hope you have a good one and enjoy. Hello there. Today we're going to talk field irrigation. Design an irrigation system that is expandable and isn't locked into one cost every time you do it. The way I've been doing irrigation for a while is a tote, a few plants, a drip line between with emitters. I ran into a problem when I was having a lot of plants that all of a sudden the drippers at the end ran out of water. And so there was some issues with health, and some plants were dying, other plants were doing really good, but there was an issue with even delivery of water. It turns out that's because my irrigation design sucked. So quite a few years later, many revisions since then, I'm finally getting a hang on irrigation. So the main thing about the expandable system is, why do we need to expand it? Why can't we just keep on adding, drip line and drip line and drip line down the line if I want to expand this direction? Well, that's the whole point of irrigation design. You actually got to sit down, think about what you're irrigating, think about how much water you got coming into the pipes, leaving the pipes, and how much water your plants actually need. So that's what we're going to talk about. So in my opinion, irrigation can be broken down to an extremely simple formula or concept, and that is, there has to be more water coming into your irrigation system than there is leaving your system. If you have more water coming in, you will not have an issue. Or if your irrigation system has the ability to handle more water than is leaving it, then it is good design. Now, we all know what would happen with this stream of water and a bucket with a hole in it if I just started drilling holes all over the place, okay? And so, eventually, we'll call this, sorry, hang on, let me back up a second. This is almost full, okay? We'll call this our water pressure that's going into the irrigation system is totally good. We only have one plant right now that we're watering, okay? Now, if I want to add another plant, I got to add another hole. And if I want to add another plant, I got to add another hole, and so on and so forth. And eventually what would happen is water would start spraying out the bucket so fast that this stream of water wouldn't be able to keep up with the loss. And that's the irrigation problems that I think is the biggest issue, and is probably the most common mistake that I have made, and I'm guessing other people as well. So how does this problem happen? If we have our irrigation system and we're just watering some plants, and we have a water source supplying water to our irrigation system, how's the problem happen, right? So the problem is that we think that this water pressure is a lot, okay? The thing that we don't think about is the total addition of all the holes in the system, okay? So that looks like a lot of water coming out, but what if the math of all the holes that we're emitting water from equals 4 times this amount of pressure, and we just can't keep up? So that we just stab the bucket full of holes, full of holes, full of holes. And no matter how much water comes out of this, because it's limited to the diameter and to the water pressure that exists here, it would never be able to keep up with the system. That is the mistake that I have made. And so you could think of it of doing some as this. That's a lot easier to visualize. That's not a lot of flow at all. And if there's a bunch of holes just shooting the water out, we know that this flow wouldn't be able to keep up with our emission requirement of watering the plants. The big difference between city water and living off grid and what have you is for sure the pressure. Unless you have a pump providing everything, you're going to have to deal with just the different diameters of pipe in order to keep yourself sane and make sure your irrigation system works. You can most likely make up for a lack of diameter with water pressure, right? Because you can just push tons and tons of water through at a very quick rate. And even though the hose can't handle all the water that's being drained from it, it's being replaced faster than it can be taken by the pump. So how do we design for something like that when I don't irrigate with the pump? My pump that I spent all my money on is powering my house so I can wash dishes in the kitchen with water pressure. Plants don't need water pressure, okay? Humans need water pressure because they need to make up for something. Now, you design for low pressure or gravity irrigation or IBC2 irrigation by following Mother Nature's rule of water reduction, okay? Ocean, huge river, creek, puddle, teeny little drops. You want your giant source of water to slowly reduce diameter, with the smallest diameter being the point of emission on the plant. And if you follow that pretty simple rule of having your largest diameter stuff here, reducing down to the next larger diameter for any sort of header or large piece that is the river, really, that feeds the creeks, you won't have any sort of weird problems that are hard to figure out. When you start up in diameter when you don't need to, you run into all sorts of really weird problems because fluid dynamics are crazy. So how would I irrigate this system in the past if I was just going to get it done? Okay, I would probably run a hose right here from the IBC tote with a valve going all the way across the fields, and then I would like tee off, and have emitter lines here or drip tape that would go to each one of my individual plants that I would plant in the rows. And then I would pretty much call it. With a few rows, that design would probably work, but as you scale up and start to do the whole field, you would run into an issue with water theft from one line to the other, because you only have one line and all different, 14 straws drawn from one line that's the same diameter. And so if we were to look at it, water would be stolen at different random times from this line here, because imagine like 10 people trying to drink a milkshake, like one milkshake, okay? That's exactly what the problem you'd run into is that you'd all start drinking the milkshake, and then eventually one person wouldn't get any in their straw, and then another person wouldn't get any in their straw, because the remaining liquid in the vessel is just being distributed at random at that point, not necessarily evenly, because of different physical aspects. somebody is drawing harder over here than over there, the slope changes some pressure here and there, blah, blah, blah. So we know that we need to stay the largest diameter possible for as long as we can to maintain as much available water so that all the little straws that are sucking off of it don't get dried up. So how we do that, we can't necessarily go to a 4-inch piece or anything and hope we're going to be getting water pressure from nowhere. You pretty much have to go with what you got unless you're using a pump. All right, this is not for designing with a pump. If you have problems, go add a pump. There you go. Your problem's fixed. Okay, now for the system that doesn't use any pumps, it is 2-inch diameter. Therefore, that is our limitation. We could go smaller, but we're trying to keep the biggest diameter for as long as we can. So therefore, we leave the 2-inch connector on it. We're then going to have a T, which is going to slide over all this junk like this, and it's going to tee off. Why? Because we have 2 fields. Then we're going to elbow over, keeping the same diameter as long as we can, to go to that field, another elbow pointing this way to go to that field. Now we have the same diameter of water being split equally between the 2 fields. Okay? Then, if we were rich, I would keep the 2-inch pipe running the entire length of the field all the way to the end, because I want to expand, right? So my irrigation can just continue this direction, and I'll just keep on adding fields that way. It would be nice because I wouldn't have to continue adding water totes or continue adding, all the parts again. I would just add on at the end. So I did say if I was rich. I ain't. And so in this case, after the elbows, or the 90-degree elbows right here, that direct the water east, we're going to go to what's called the header. Now the header is normally the long piece that is at the head of the field, or like a headboard on your bed, the very end of it, where everything splits off of. Another word for it you could think is like a manifold. So we're going to run a smaller diameter than this, as big as you can go, as big as you can afford. That's all I can say. The bigger the better. Okay, if you had a 2-inch pipe going here, that would be awesome. Now, for my design, I went with 1-inch pipe. It's a really big price jump from 1 inch to 1.5, and also where I'm at, all the fittings for 1.5 are pretty much impossible to find, but the whole aisles are stocked to the brim with 1-inch fittings. So in my situation, it made sense to go with those. Again, I don't want y'all to get lost in the exact pieces that I'm using and everything, but the main concept of going from, again, to use the Mother Nature perspective of ocean, river, creek, whatever is smaller than a creek, going to all the plants, okay? 2 1-inch pipes are going to be running right here, 22 feet for the fields. I have a different number of rows in this field than I do in that field up there. And so what I'm going to do is take measurements on the exact distance between the fields and cut the pipes to length there. I then have a T which will divert the water down here. This is normally where I would put in my drip tape, okay? Because I have huge diameter, 2-inch diameter, 1-inch diameter header. Drip line is 5/8, which is a little over 1/2 inch. And so my reduction is going in the correct order. And then the drip tape, or the drip line, which is 1/2 inch, the black stuff, would go all the way down here on a row. be capped off, and then I would put in my emitters wherever I needed to along the line. So by putting everything in that sequence, with the water over here in this corner, reducing down to a giant header here, reducing down to the drip tape, to then the emitters, it allows itself to be expanded this direction. You see, because the headers will just be sitting right there. And you can then, as you get your fields installed, just add 1-inch headers to the end and then stretch it out. And then all you do is go cut your lengths to the T's, wherever the T's need to be for your rows, and then repeat it. And again, if you tried to repeat this infinitely, you'd eventually have to get tons and tons of totes of water or get a pump, because your system would be at its physical limitations, which you'll know because all of a sudden stuff will not be doing very good anymore. All right, so now I'm going to go ahead and bust out the pieces and we can see what it looks like. So the adapter goes from 2-inch to the tote. Then we have a T, which splits for the 2 fields. Now we need to reduce to the header size from the big 2-inch main, I guess you could call it. And in order to do that, you need what's called a bushing. And there's 2 different types that I have run across. The most standard type that I get from the big box store that's blue is this one right here. You can see it has a bunch of, I don't know, bars or ribs or gussets on the side. And there's actually a big hole around before it goes to the exit. This one is awesome and is sloped the entire way. It's like a funnel. So every drop of water goes right here. If you can, I really recommend getting this kind of tapered funnel type bushing because it's much better for our application. And if possible, I'm going to actually replace this one, which is from Lasco, with the other type, which is from Spears, because it's awesome. When the field's all said and done, the water source is going to be exactly in the middle so that the main can straddle the fence line. Now, once we have these reducing bushings installed, they go to whatever size you want your header to be, okay? And the biggest you can go, the best. If you could stay 2-inch the whole way, do it. Now, I have reduced to 1-inch. I have also, because my fields are very specific purpose, I've color-coded my header lines. PVC is not UV sealed or UV cured or anything like that. It is susceptible to UV, that is sunlight damage. It gets brittle, it breaks, it shatters with age if you do not coat it. So all PVC you buy in the store most likely needs to be painted before you use it in the field, unless you're going to cover it with cloth or something like that or bury it. Now, you can just paint it whatever color you want. I like things to look a little different. So my rhubarb field, which is the bright red one, is the field I'm standing in, and the strawberry pink one is, for you guessed it, strawberries, going in this field up here. So the header pipes, sorry, I'm just kind of moving this around. It's going to actually be closer to like that, okay? Because that's the center line, and then you come down here. Header pipe connects to the reducer. We then go the entire length of the field because this header pipe is what's going to be supplying the water to everything. So what comes next after the header is the actual T that we are able to thread into. This is a 1-inch T by 1/2-inch threaded. It's also called a spigot valve because, or sorry, not a valve, a spigot. Spout, not sure what to call that, because it takes a spigot, standard sprinkler fitting, so it's really cheap as well. So we have a T come off every single row we can. So we go over here, we have a T. We go over here, we have a T. Then we'll notice, oh no, we ran out of space. It's because these links have a set length to them, and I wasn't able to find 22-foot long sections. Manufacturer doesn't make them. That's why they make this coupling. So this slips on the header pipe. When you get to the end of it, you then go grab the other side of the header and put into the coupling. We then go over here, and there would be a T. And then there would be a T, and then there would be a T. And you'll notice the pipe looks a little short, but don't worry, because we're going to be cutting these links where the T's are inserted, and it's actually going to add just a little bit to the length of the overall header each T we install. I think we'll be just fine. Actually, after this reducing piece, forgot the most important thing, a valve. Reason being, it's not needed, but I like it because it allows me to control what field I water. If I don't want to water the rhubarb field, I come here and kill this. If I don't want to water the strawberry field, I'd kill the other one on the other side. So almost done with the header. The very last pieces we're going to need is, at the very last row, we're going to need another section of PVC standard pipe coming over here to the end of the fence line, and I'm going to install one of these right here. It is a 1-inch coupling with a reducing bushing installed. So it's a 1-inch by 3/4 reducing bushing that is threaded by slip on the outside, and this allows me to thread in a hose adapter. This is pipe thread on this side, hose thread on this side. So I will have my header laying here, and then this will be sticking out the fence, and I can have a hose bib threaded on it with a stop valve, and then I can do any sort of irrigating outside. I usually have like herb pots and stuff lined up on the outside of fences or what have you. And that's going to end it for the header for one row. So now we've mirrored it on the other side in the strawberry field, and that's going to have a greater number of rows, 8 as opposed to 6. So we do the exact same thing. We have a valve coming off of that, going into the header, and every row we're going to tee off with a spigot threaded 1/2-inch thread right there. 3, 4, it's right before the coupling, it's no problem. There's another row, another row here, and then I haven't put in the last row yet, but it's going to be right here at the edge. And I'm going to do the exact same thing with the very end of the header, and we're going to put a coupling with a reducer bushing to 3/4, which goes from pipe thread to hose thread. So I can tap water, maybe even put a drip line irrigation to the outside, and make the herbs live that way. Lots of options. Now I'm going to go over exactly how we connect the drip tubing to the tee that we just set up. So, of course, these are going to be cut and inserted onto the whole line. We get these 1/2-inch male pipe thread by 5/8-inch insert male adapters. Looks like this. This barb fitting is what we slide into our drip irrigation hose that we then put in the emitters, which drip water on all of our plants. The T's for the header are reducing T's to 1/2-inch spigot, which is the standard irrigation size for sprinklers. So this threads right in there, just like that. Nice and simple and elegant, and then this will slip on the barb. So once they have the drip tube installed, you would basically anchor it in if you need to, depending on the soil type you're put into. I definitely would need to anchor it with this really old hose, which has a lot of memory in it and is kind of a weird shape. You'd go in, punch your hole, and put your emitters along however wide or the distance apart that your plants are in the field. I recommend probably drip tape is really nice, but if you're going to be doing gravity water with fed from an IBC tote, gets a lot of mineral buildup and is very difficult because it clogs very often. The length of the drip tube would be run the length of the field, capped on the end, and left a little excess so you can clean any gunk that builds up out of it. Just go cheap with the pipe tie. Don't bother buying those fancy caps they try to sell you. Now, that's it for the main system. We have a main coming from the tote, as large a diameter as we can. It reduces down to a header bigger than the size of the row drip tube we're going to get, which means bigger than 1/2 inch, smaller than 2, right? And well, smaller than your header. Then it comes down to our drip tubing with our emitters for the plants. And that's pretty much that for the system. By following the basic concept of largest, larger, large, medium, smallest, we can keep a nice system in mind. So how do you go about calculating the actual water that your chosen system or system design can produce, and how much water is moving through the pipes? Main thing you need to know is it's not intuitive. For instance, 1/2 inch pipe and 1 inch pipe. 1 inch pipe is, yes, twice the diameter of 1/2 inch pipe, but it's not twice the available water area. And this is where it gets crazy. So if we look at the curve of how much water each diameter can hold, it is a J curve, which means that it exponentially increases the larger the diameter you get. It is not a linear function, or it is not a perfectly straight, expectable number. So here's the math. 1/2 inch diameter pipe has an area of 0.19 square inches. Pipe that's twice as big as this is 1 inch pipe, has an available area of a little over 3/4 of a square inch. That's 4 times almost this number, not 2. When you get up to this diameter, it happens to equal pi, which is really easy to remember. 3.14 square inches of available area for a 2 inch diameter pipe. And again, this would be assuming that the 2 inch is the inside measurement, and it's exactly 2 inches. So by taking these numbers here and plotting exactly the difference in available area, or available, I would call it like the cross-sectional water column area of the pipe diameter. So you can see that if you could, you'd probably want to get 6 inch diameter or 5 inch diameter stuff, because the amount of water it can hold is just astronomical. It's also going to be astronomical in price. And so when you have all this available, you can just kind of pick and choose, right? But we're sticking to the math here. So let's go ahead and calculate out the exact system that I have set up and how much water is available at each T. Well, I can tell you now that my system is limited to the smallest point at that T. And so it's 1/2 inch. That means I have this much available area of water coming out per cycle of my 1/2 inch spigot. Now there are charts for all this stuff available online. I suppose you could just go look up PVC pipe water capacity tables, and it'll give you most of this information. But I found that it varies per manufacturer, and I like to get a more exact idea. Also, if you got the pieces at hand, you can just trace them on a piece of paper. There's no need to look up any tables or anything. And if you got, like a tape measure, a layout tape or anything, you can check all the math yourself. So we just need to go back to 7th grade or 8th grade math, which is just a little bit of geometry. We're just trying to calculate the available area of a circle, which is going to be how much water a different size pipe can hold. Okay, so I've gone ahead and traced each component that I'm going to use in my system. I have a 2-inch piece of PVC, ½ inch, 1 inch, 3/4, an emitter, and this is an adapter that goes onto my threaded T-fitting down to the drip tube for, I guess you'd call them the branches off of the main header. Now, why would you ever need to calculate this? Well, one of the main reasons is what I like to call water theft. And so if you had this line being your header across your field, and then this line coming off of it 20 times, you would understand that there's a huge issue. It doesn't make logical sense to have something this large after this, because this would require too much water from this line. We intuitively know that, but there is, of course, reasons for it and math. So in order to calculate the area of a circle, the formula is area is pi r squared. It's like the most basic one from geometry that I can remember. So once you plug that in with the information, just remember that this 2-inch refers to the diameter and that radius is half of a diameter. Even I sometimes make that mistake sometimes, and I mean, I live this stuff. Okay, so volume capacity per foot. Now that we've calculated the the available area per size, we're going to go ahead and calculate the volume. Now, how do you get a third dimension from a 2-dimension? Square inches. You add a third dimension, which would be the length of the pipe you're measuring. So, in order just to get a per foot calculation that we can use in the rest of it, we just multiply everything by 12, okay? So, we have 37.68 cubic inches of volume available per foot of 2-inch diameter PVC. When you go and start converting all that data, it equals out to almost 1/4 of a gallon, about 1/5 of a gallon, a little over 1/2 of a liter per foot. Okay, I even went as far as going to check teaspoons because I'm curious. And I mean, what does a fraction of a gallon mean to anybody? Like, 0.022 of a gallon, what even is that? It's 17 teaspoons or whatever, so it makes a little more sense. Once we go fill the table out for all the different diameter pieces we have and the available volume in cubic inches per foot, we get all the information on their capacities. And then we can plug in our data from the field design that we have to figure out exactly the weights and measures of everything. The most important piece of information for me that I'm trying to figure out is the total volume of my header and its capacity in relation to the branches that come off to it. I want to make sure that I'm not going to experience any sort of water loss or water robbing just based off my design. So what I did is for my header, I took the available area of the pipe size I'm using, which is 1 inch, and it has 0.785 square inches of area for that size. I then multiplied it by 12 to get how much available volume a 1-foot section of 1-inch pipe has. It turns out to be 0.005 of a cubic foot. If you go up here, you can see that in our little chart we made, which is 0.04 gallons. Now you can take that number and just plug it in here, and you will get 0.88 gallons per 22 feet. The 22 feet represents the length of my field that I am installing the header on. Okay? So that means for a 1-inch pipe, 22 feet long, there's almost a gallon in it. That means that each of my headers will have a mass or a weight of almost 8 pounds. I'm pretty sure that I can take 8 pounds and tie it to my fence no problem so that my header is above my fields. So that's great. For the branches, it's a little trickier because you just have to go to the adapter we're using to install on the drip line. And it's 1/2 inch OD, and the inside is, less than that. It's like 0.2 or something like that. And then the drip line, when you measure it, ends up being 3/8 of an inch. So when we do the math, 3/8 of an inch equals out to 0.110 square inches. That's the available area of water that can travel through this hole. Now, each of my branches on my field, if this represents my field, each of my branches is 25 feet long. So I then can calculate out exactly how much water a 25-foot long drip line has available to it. So for the drip system, let's just say that the entire drip tube's like 3/8 diameter, because it's hard to measure a tube that flexes all the time. We'll plug that in here to get a total volume per foot of 1.32 cubic inches. That ends up equaling out to 0.0057 gallons per foot for the drip tubing. Okay? If we then take that number and multiply it by 25 feet, which is the length of each of my branches, we'll find that we can get 0.1425 gallons in the entire 25-foot length of the branch. That's actually, to me, very surprising, because it's really close to this number up here, which is 1 foot of 2-inch pipe. So 25 foot of drip tubing is equal to 1 foot of 2-inch pipe in volume. It's very close to it anyway. So let's move on to the next part of it. So now, in order to find out if the header design's adequate by number, we say, okay, my header, 22 foot long, holds almost a gallon, 0.88 of 1 gallon. My branches, 25 feet long, hold 0.1425 a gallon. So we know automatically that my header can handle 1 row without a problem, right? So then if we just take this number, divide it into 0.88, we find that we get 6 and a fraction, meaning that 6 branches is equal, roughly, to 1 header, which means that my strawberry field, which has 1, 2, 3, 4, 5, 6 rows, is never going to run into a supply issue pretty much ever, just based off of those two numbers. Now, if I tried to put a bajillion holes in this, that's a different story. But the header and this length and size is totally fine. Now, thank you, Wind, for turning the page. The emitters are a little bit trickier, okay? Because the hole is a measurable diameter. However, it just drips out every once in a while. It's not a constant stream. And so you'll have the same size hole for the emitters for various gallons per hour or emission rates. So because there's what I would call like a turbulence flap or a diaphragm inside that causes the water to take a long path and then drip out, as opposed to just spraying out the hole, right? Because that would be not a drip design. So we just have to calculate in gallons per hour, which is the number given to us by the manufacturer, and we have to trust them that their math is correct, unfortunately. So it's actually pretty easy, though, because you just take, alright, on 1 row of my field, for rhubarb, I need to have a dripper at X gallons per hour, and then how many plants can I fit on a row? And then same with the strawberries. And then that gives you your total watering consumption requirement per row. And then you can end up doing it for the entire field. So here's the field. Has a water supply in the form of a tote, which goes to a main, which is the branch, splits it into my 2 fields, a rhubarb field and a strawberry field. The headers, which are 1-inch diameter, supply water to each of the branches which will feed the plants at a specific spacing. Now, strawberries are recommended to be spaced 18 inches apart along the row. Their rows are recommended to be 30 inches, almost 3 feet apart. Rhubarb, the distance between the plants, because they get much larger than strawberries, is recommended to be 3 feet. And the distance between rows is also 3 feet. Now, by getting this information, we could set up the field to be exactly how we need it by getting the XY spacing. But this is the only number we're going to need right here, is the number of plants per row we have, because I've already done the math to divide them. So, rhubarb, let's check it out. Alright, 3 feet apart. I have 25 feet. What's 25 divided by 3? Let's see, it's not 8. So it's probably going to be 7. 7 times 3 is 21. Yeah, so it's 7 and a fraction. So I know that on this row, I'm going to have 7 rhubarb plants. Then, how many rows do I have? 6. Oh, you know what? I inverted these fields. Whoops! Goof is fixed. My rhubarb field has 6 rows. My strawberry field has 8 rows. So, if each row of rhubarb holds 7 plants, that means the total amount of plants I have for that field is 42 plants. Now, let's say I'm using 4 gallon per hour emitters. That means for 1 hour watering, 168 gallons per hour. That's half a total water for one field. Now, doesn't mean you probably shouldn't use 4 gallons per hour emitters. Now for the strawberry field, we have 8 rows at 18-inch spacing. That ends up being 1.5 feet. Alright, so we can take 25-foot field and, get the spacing for that. And we get a total of 15 plants per row. And at 8 rows, that's 120 plants. 4 gallon per hour emitters, you'd be using 480 gallons for an hour watering. That means your tote would run out in the first half hour. So, that's how you calculate out exactly how much water your field is going to consume based upon the emitters that each row will have based upon your plant spacing. You can see there's a really big difference between these two fields just because of the sheer number of plants that they have in them. It's not to say that because these are huge plants they will use as much water as this one, by any means. We'll have to see that later on. We may already reached it for a lot of people, but this is where the math gets kind of not pointless, but just to calculate out certain things like number of cycles that your system can push through before you're out of water on your tote or anything like that. So in order to know exactly how much water is in your system, you actually need to do the math for the physical geometry of the pieces that you're putting together, right? So we already know the capacities and the area of all the different pipes, and by plugging them in and breaking down the different segments of like the main connections and everything, we can get the exact length and therefore volume that each portion of the system holds. I'm not going to go into this equation. I'm just going to put the pictures here and hopefully it's self-explanatory. This is for the main. For the header, might need a little explanation. The entire length of the header is equal to the pieces of header pipe I have plus the T's I have in there. The pipe slips into the T, but it doesn't change the overall length much because all it's doing is actually adding this segment here where the thread goes down to the adapter. So in actuality, it's a really simple equation in that the length, if we had 1 T in it, would be the length of my pipes plus the length of the spout coming off the T. And that would be the entire volume that the header would hold. Now, if you want to calculate for your exact system, meaning the number of T's you got in, you just toss in X and substitute it for the number of T's you have. And that's that. Now, we probably actually need to solve this one out. Alright, so if we have a header for my field, the length is 22 feet. For calculation's sake, we're going to use 20. Alright, so that would be A. Two 10-foot sections. The header is 20 feet long. So we're trying to find the length. So we put in, for A, it's going to be 20 plus, how many T's do I have? Well, first, I got 2 fields, so I might as well label these. This is going to be the rhubarb field calculation. I have 6 rows. So I have 6 T's. So X equals 6 in this instance. So it's going to be 6 times this dimension. Let's say it's... Oh, what happened to... No, that's not a 3/4 one, dang. Believe it or not, I was actually able to find the T I'm going to be using. Okay, so this T represents this T. And so if this dimension is... It looks to be an inch. So it adds just about an inch or so to the length. That makes it really, really easy. So B is going to equal 1. So then we can multiply 6 by 1. And this is going to equal 20 feet plus 6 times 1 inches, which is 6 inches, okay? I think we know that that's 20.5 feet. So, for the rhubarb field, with 6 rows, 6 T's, each T adds 1 inch in overall length to the header, we're going to get 20 foot, 6 inches at the end of our pipe. Alright, for the strawberry field, let's go ahead and use the real calculation. Still 20 feet. I can't stretch the pipes. I'm still looking for that pipe stretcher, board stretcher. So it's 20 feet plus, this is the T quantity. The strawberry field has 8 rows. 8 rows. So we know this is 8. We then multiply that by how many shoulders are added to the length of the header, and that's 8. Sorry, it's 8 shoulders, 1 inch length, and that gives us 20 feet, 8 inches. And there we have it. Different number of T's doesn't really change the overall length much, but when you start adding a whole bunch more rows, it definitely would. All that'll change is the overall weight of your system. It doesn't matter too much in smaller diameters, but if you're dealing with larger diameters, that extra weight could definitely make a difference. Alright, well, it wouldn't be math time unless we did some review, right? So what have we learned exactly? Well, we learned that we can calculate the capacity of different diameter pipes, and by multiplying out their length, the actual volume in gallons or liters or teaspoons that each pipe can hold per length. We took that information and plugged it in to for our header and our branches, and we found that our headers coming off of our 300-gallon supply hold almost 1 gallon. So we have to add 8 pounds to the weight of each of the header, which means our fence can handle it no problem. So my plan of being able to hold the line to the fence with some ties is going to work. Now, also, we found out that if I use 4 gallon per hour emitters for the rhubarb field and the strawberry field, in the rhubarb field, I'm going to be out of my tote in 2 hours. In my strawberry field, I'm going to be out of water in my tote in 20 minutes. So I'm going to need to do some adjusting on the emitter types that I choose and get out some drip tape or something and figure out some actual calculations per foot. That's why drip tape's really nice for agriculture, as it's rated in gallons per hour per foot. So once I narrow in on that, we'll go ahead and choose an emission and get an exact number that is nice and friendly to our water source. I'm not going to try and go in to refill the tote every day because, one, the water would be wasted by just being dumped on the ground and not absorbed by the plants, and two, yeah, that's actually the only reason. So you want to know the funny thing, and I really appreciate you sticking through this really long and dry video. All of this information could be obtained without scribbling one number on a paper. You can go out there, put all the pieces together, right in the field, dump water into it, fill the system up, put on the fence, see if it'll hold, get all your water and your drippers out and install them, and see, oh crud, I ran out of water in 20 minutes on here and 2 hours over here. I guess I need to change out my drippers, you know? You can do all this without any calculation, but one thing is, for a small field, it's not a big deal. But could you imagine this type of error here on hundreds of acres if they bought the wrong drip tape? You know, they would flood their field. They wouldn't be able to raise their plants correctly because they're getting too much water. You know, there's reasons to go this crazy and calculating stuff. I hope you have a wonderful day. Enjoy doing irrigating stuff or designing your system or what have you. If you find any errors or anything in this, please let me know. Math is not my strongest subject. I'm a drafts person, so I'd be glad to correct them. See you next time.